Hello students, welcome back. Previously, we went through a couple of examples on finding CDF from PMF, and those are actually very important examples. Now let's go to even more important example, finding PMF from CDF. Let's go backward. So, previously we talked about from PMF, finding CDF. Now let's go backward. From CDF, finding PMF. Which is easier? From PMF to CDF is easier. Going backward is harder, but more important. Okay, here we go. Find the probability mass function from the given cumulative distribution function. So here we have CDF. So we have the class intervals, and then 0, 1/3, 1/2, 3/4, 1. We have all these. And please note that we have cumulative probabilities from 0 to 1 steadily increasing because I keep adding up the probabilities which are positive. I can never go down. You see? And always I have to increase from 0 to 1, which is indeed the case here. Now, exactly where am I getting that jump? I'm getting jump at 0.25, which I'm highlighting in a certain color, blue. Next, I'm getting another jump, second jump at 0.5. And then the third jump at 1.25. And then the fourth jump at 2.0. Can you see all that from this table? You can see the same thing. Either you get this vertical tabular form or horizontal tabular form. In horizontal tabular form, it's a little bit easier to see because you can readily associate it with a number line. Let's see. With the number line, let me see. Okay, I don't have those already prepared, so let me go to drawing mode. So let's suppose we have this number line here, and then 0.25, and then 0.5, and then 1.25, and then 2.0. Because this is in horizontal tabular mode, it's a little easier to associate appropriately like this. And then up to here, of course, nothing. And then something will take place here, so I'm going to get a certain jump up to here. And then another jump, and then another jump, and final jump, and then this will go to 1. So start from 0, jump, 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 and then going to 1. That's what you can visualize from this table, as a matter of fact. Exactly how much jump is something you have to calculate. Not too bad, but you can visualize this with your brain. Even if you cannot visualize, well, take some space like this and get a piece of paper and ruler and draw something like this. And that's going to be helpful. And the threshold, 0.25, 0.5, 1.25, 2.0, yeah, you can have all those. And you can even do color coding. And then you get appropriate jumps. CDF is a step function, so you're going to get jump. Exactly what is the size of the jump is something you have to determine, but there you go. The preparation is done. Okay, now that we got all these, let's figure out the size of the jump. At x equal to 0.25, we got from 0 to 1/3. We got this. So what's the jump size? From 0, I jumped over to 1/3. So what's the jump size? By 1/3. To be a bit more precise, it's going to be 1/3 minus 0. That's the first observation. Next observation, at x is 0.5, from 1/3 to 1/2. Jumped by how much? 1/6. To be a little more precise, 1/2 minus 1/3. And next, from 1/2 to 3/4, we jumped at 1.25. And finally, from 3/4 to 1, we jumped at x equals 2.0. So you have to do 2 more of these, and you can figure out the jump size. If you do all those, you're going to get this. You see, you're looking for these jump sizes. From here to there, we jumped by 1/3. From here to there, we jumped by 1/6 by subtracting. From here to there, I get jump of 1/4 by subtracting. Finally, from here to there, we jumped by 1/4, excuse me, again by subtraction. So what do we have? We have repeated subtraction. Do you recall what we did to get CDF from PMF? We repeated adding up the probabilities. Remember? We added up because we wanted to get cumulative probability. So cumulative probability, so you have to accumulate. Keep adding up. Now we are going backward. Going back from addition, we have to subtract. We keep subtracting. But subtracting what from what? Well, graphically, we are looking for this jump, and that jump. And this jump, we get it by subtraction. This jump again by subtraction. This jump again by subtraction, like this. This picture was drawn up to scale, so it's a little bit difficult to see. I mean, too accurate. Especially when these intervals are so short and there's so much attached, then it's actually difficult to see. But the crude picture I showed you before with this drawing function, that's actually better. I didn't draw up to scale, so I can freely put any kind of subtraction in there. And the subtractions are these. Subtract, 1/3 minus 0, subtract 2/3 minus 1/3, 3/4 minus 1/2, 1 minus 1/3. So we get these jump sizes, and those corresponds to the probabilities. Otherwise, all 0. And once you get all those, make sure if those check out. If these add up to 1, please check. And then, even better, from here you can get the CDF again by accumulating and see if you get this original one back. This kind of problems are a little bit harder and also a little bit more important because you have a little bit more to think about. And also, without sound knowledge on the forward problem, you cannot do the backward problem. So if I write a backward problem, then I'm testing not just this problem itself, but your knowledge on PMF to CDF, the forward problem as well. So this kind of problems are more comprehensive. So I have to say it's more likely that you're going to see these kind of problems in the exam than the other way around. But of course, not 100%. If I add up these two, PMF to CDF problem, and then CDF to PMF problem, if I say either one of these two problems, then the chance you're going to see either one of these two problems in exam 1 is nearly absolute, nearly 100%. And then if I divide among them, about 3/4 will be CDF to PMF, and the other 1/4 will be PMF to CDF, maybe. So we just went through an extremely important class of problems. By the way, I have the same problem, exactly the same problem, written in terms of piecewise defined function expression. Looks a little bit more intimidating, but this problem is not different at all from this problem here, given in horizontal tabular form. How do I get that? Well, at x equal to 0.25, we have a jump size from 0 to 1/3. Subtract. And at x equal to 0.5, I have a jump from 1/3 to 1/2. Subtract, and so on. So like these. And at blue, red, green, and brown points, at 0.25, 0.5, 1.25, and 2.0 at these points, I do appropriate subtraction. And those are going to be the probability masses of the probability mass function. The original function was given in terms of this piecewise defined function expression. So the answer also was given in piecewise defined function expression. But if you prefer to use tabular form as the final answer, go ahead and do that. It doesn't matter one way or the other to me. All right. So we went through a couple of extremely important examples, finding PMF to CDF and then finding CDF from PMF. So if I go back to over here, conceptually, what does that mean? What do you mean by probability distribution? Originally, I defined like this. PMF and CDF put together as a single entity, and I named it as a probability distribution. It turns out, however, that you don't really have to know both. If you know PMF, then you can find out CDF. And also, if you know CDF, you can find out PMF. So these two problems are conceptually not different at all, these functions. So no wonder you can put together as a single entity and call it with just a single name. In my case, I use the term probability distribution because, as I just said before, essentially PMF and CDF are not different. They actually point toward the same concept. What's the name of that concept? Probability distribution. Probability distribution of a discrete random variable is called discrete probability distribution, and we went through those rather thoroughly in section 2. And then we're going to do a little bit more applications of that in section 3, 4, and 5.